Okay, so let's start the course on astronomical spectroscopy. And I mean, the idea of the first few lectures, I think I initially preferred to only 2 lectures to cover it, but I don't know, maybe I'll active a little more and take a bit in the second half as well. So, but we tried finishing 3 lectures and then we have it sent tutorials, which will basically give an idea about what you learn in these couple of classes. So my responsibility is to, give a basic idea about the spectral atoms, atomic structure, and just to begin with the spectroscopy. Yeah, I mean, these part you might have already done in your course. These were so we know already undergraduates here. Chinese. Okay. So probably you might have done a bit of it, but then I think the first part you might have done it, but then this is time for what you actually learn in your MSc, in your BSc or in the undergraduate program. So let's start with simple definition of an atom. Do this like it says very young. But then the spectroscopy actually starts when the atom itself. The atomic spectroscopy. So we need to start with the atomic energy levels and then how does emission or absorption spectroscopy works. So let's start with simple atoms because atoms are important, but we know that. Say, let's start with the first simple historical overview. This is not, it's just, we already know about this because we have atoms being defined in some text by Canada in 6 BC to around 6th century BC to around 2nd century BC. It's already in the Indian text. And if you go here, it's not developing the foundations as an atomistic was. Okay. And these texts are called Vaisheshika Sutra, which was already there in Indian literature. And then you can, they also talk about Guano and what is the atomic molecules and trionic, which is basically atomic money. So it was already there. And in 5th century, basically 3rd century BC, we had Lysippus and Democritus who talked about if you talk about the main atom, which basically comes from the indestructible entity, that the word atom comes from that. Like the phenomenon is basically, in terms of science, it's the indestructible entity of the universe. And then in 1803, John Dalton took this particular text where he defined elements, actually. That's the first time we talked about elements, atoms as elements. And then somewhere if we can see that somewhere the formation of molecules. Now, even in Sanskrit text, Vaisheshika Sutra, which was defined, it is clearly mentioned about chemical reactions between atoms. And they give the examples like, when you burn something in a pelt, the paper, the blackening of the pelt, they talk the sort of chemical reaction to say it's kind of a, reaction between atoms and forming something else. So these were already discussed. So these are some of them. And then we have the attention, we came up with this plum-feeding model, which was also not very effective. And then Rutherford came up with the planetary model to describe the experiment done by Gilbert and Millett by Boston in 1999. Okay. And she used this alpha-particle scatter on aluminum foil and tried to describe how atoms look like. Because so it is the idea of looking at the structure of an atom. And the other individual of the model is, as even in classical theory, there's one that when a charged particle is accelerated, it can radiate energy. So since the electron is moving around, it's changing its direction every instant, which means it's accelerating or decelerating, depending on the velocity and the speed of the electron is. So if you did that, only this changing it's accelerating means momentum is changing and you have uh, energy has to be released. And when it releases energy, the energy at the electron decreases, and that makes it come closer and closer to the nucleus and finally fall into the nucleus. Okay, so this model doesn't work, but yes, because we are standing here and this flow because it is down, right? It is solid up. Even though the other have said it's energy, but still atom is strong enough to harness to this surface because everything is made of atoms. All that. And then we had the theory of Niels Bohr in 1913, and if you can, the plasmids are electrons in atoms orbit the nucleus, which is same as what we talked about, that they can orbit only as orbits terminally without radiating, and these are called stationary orbits. So this is something which try to induce them deliver for scattered model. And you can see that when you get an energy to the atom, it can get excited to the higher level, and then it releases energy after some time, it comes to the lower energy level. And this is what we are going to learn about the spectroscopy. And this is the spectroscopy of atoms, which we are going to learn. And of course, the angular momentum of the electron is quantized. Okay, so these are the plasmids of Bohr. And then this is called a semi-classical approximation because it's not clearly mathematical. He has pursued some ideas and tried to use the existing knowledge to develop a theory, to develop the idea of the structure of the atom. So when we talk about spectroscopy, one thing is very clear. Why do you need it? Can we look at the nucleus? Can we look at the atomic structure? Can we look at anything which is beyond our visible, in the space which is very far from us? So for example, if you want to look at a star, and I've tried to predict what kind of animal is present in the star. How do you do that? That is the astronomical spectroscopy which you are doing there. You look at the emitted light by the element in the star, and when you look at the spectroscopy and try to find out what kind of environment it is, and then you try to match it with the particular de-excitation or efficient light in a system which you already know, and then we compare it to say, here, some other item element, and say that, okay, the abundance is this. This is the abundant element in that particular star region. So this is how the spectroscopy works. So that's what we are going to do. And then we have this very unknown center field, which I'm not going to, and then finally, I have the model, which is by Schrödinger is, of course, that is important because if you look at this picture, what is wrong with this picture? That is the first picture I showed in the presentation. What is wrong with that picture?
Yes, it's to do like this electronic dipole, the conception, knowledge.
Okay, that's not the year, or the electron doesn't have any shape, like you can measure, because it's too small to measure actually. Then what is this? What is wrong with this picture? This particular picture. These subparticles, fixed orbitals, okay? Yeah. Yes. Yes, I'm going to do it.
It's your body.
Now, quantum mechanics is okay. So we got subatomic particles, that is an electron. The shape of the quantum mechanics are classical. This is a classical picture where fixed orbit, as you said, and we know where the electron is. Which is not possible because of that certain principle. So the picture is not like this, but we'll come back to that picture at the end. Okay, so that's going to be so. In terms of when you look at the Schrödinger picture, electrons cannot be fixed at one position, and you can't say that's the answer of the principle. You cannot measure their momentum and position simultaneously for a subatomic you got it without having an error, an uncertainty. Okay, which is expressed by 2, which you already know. So we cannot define a picture like this for a quantum mechanical particle. So the structure of atom which you see here is not right. But then how this weird atom works very fine. Because most of the spectroscopy I'm going to talk about is the bits at the moment. How does it work? It works because when you do an experiment, when you actually see the observed result, which is going to be the best probability observation you are getting in that particular measurement. And that is, that is what is you find out the expectation value at the expectation value of a particular or theoretically call it an expectation values. The expectation value of the radius of hydrogen atom, which you already know, to the word radius. And how do you get that value? That is not fixed actually. That is the most probability value in the measurement. It should be able to get it there, should be radius, because automechanics says that electron can be anywhere. So, if it can be anywhere within the region, then you should be able to get different values when you try to find out the radius of of electron and hydrogen atom. And then, of course, this is weird because now we need to look at how does the electron is arranged, which I very you already know this, but of course we know that in case of hydrogen, you have one electron in the first level. Okay? And then when we look at the next element, we find that, okay, there is one electron which can go into that. Okay? But when we go for and place the next one, it's not like you cannot add anything to that. Now, that level is conveyed. So the first level, that is by the one is having a 2 electrons. I mean, you get a maximum of 2 electrons in that. And then the next one for the media, it had the electron going to the next. And then you can keep on going, and then up to 10, we'll see that neon will have 8 electrons in that in the second level. And then when you go to the next one, the level, atomic number 11, decide that it start with a new level. So it is 2, 8, and so on. Okay. So there is, so we use say that as you arrange electron in an atom. Now, how do you look at this statistically? Okay, so this is not the process that we are going to look at. The idea of the energy. So when you look at a spectrum, actually, we are looking at the movement as a particular radiation. Okay, so how did that explain to your lattice? That's what we need to look at now. Okay, so then you get a line that we can see now. We get a spectrum means when there is atoms, it's called line spectrum. Okay, so if you are asked the difference between the atomic spectrum and nuclear spectrum, the first thing is the atomic spectrum you get ions. For the nuclear spectrum you get bands. Bands because it is the way that simply the electronic excitation. You can have vibrations, you can have stations. And that is built within each line you'll see here. So the line is not a single line or many quick, but we have a many lines in a one single line. So let's start. So now let's say you had one electron and the lowest energy level. Okay. And if you give that energy to it, it gets excited to one of the excited energy levels. And this is called the absorption. So this is the absorption section. The energy you see and the spectrum you get because of this is an absorption spectrum. Okay? Now, of course, now it's in the excited state, which is not stable because it's about electron, so the atoms tend to come back to its normal state, or the stable state, which is the least energy state, is the ground state. So if you have some time delay, depending upon the particular level, after that, it will just come down to lower level. It can tell to any other levels before it comes to the ground state, but and just say in general, this is the picture. And we know that the energy at the emitter, so when it comes down, so here it's having a higher energy, and it is, it just, when it comes down, it is using energy, which means it has to release that excess energy, and that is in terms of this particular wavelength. That is delta E, must be the difference between the energy levels. Okay? The direction. Right. Okay. Then there is one thing. So I drawn a straight line here. So what is the difference? It is actually, can it be a straight line, city line, the energy levels? Why? The conditions. See, can it be? I said, the same energy levels, right? I've done a single line here because it's enough. And hence the balls are converted. But why is a single line? And why is this can be a single line or something else? The Maclaurin's here Heisenberg had something principle, energy and time, which means you cannot accept the measurable time and as which means if you have a bat, energy line will also be at it involves a single line if you do that. So from the levels of that energy level and the highest at the energy level, there can be small difference. So the frequency they have send the ratio, but you don't randomly see it. But this is one part which will have at least in the spectral line. Okay, but that is not very reasonable, but not very visible in the spectrum. So that's a way to mess up the spectrum. Either just other factors which will come up later. Okay, so now if you take the hydrogen atom and you put these lines, and I've drawn these lines because this is one of the line. These are the lines which you could easily see because this is a spectrum. You know the spectrum, right? Electromagnetic spectrum. And this comes within the electromagnetic discipline region. Okay? Well, so this is anicotic tool. So I said you can have anicotic when it can relax to anicotic 1, 2, 3, and 4, and so on from a higher. So here I've taken 6 at the excited state, and then it is falling to the highest one of the 6, and then falling to the anicotic. So I'm saying the lower, the final state, which is the lower one, is just, which is anicotic 2. And this line is the first line, hydrogen line, which was observed historically. Why? Because it is easier. These are the regular structure in their colors, which you can check. But other individuals of facts not observed, but we not only do hydrogen spectrum. Hydrogen spectrum is much more continental than this few lines. So then in the first line, which is the 4th nanometer, this is the line of the eye, and then you have the B line, which is the 434 nanometer, which is from 5 to 2, and then you have the 9, which is from 4 to 2, and the red one, which is from 3 to 2. So these are all the actual colors you see in the hydrogen spectrum. And this is called? This is a series. Balmer series. This is for the Balmer series, and the Balmer actually find like this spectrum, this series, initially because this is the big spectrum related. Okay, now what you actually said there is there are 3 things which we can have in terms of as a spectroscopic terms, you can have absorption and emission, right? Because this is called an emission spectrum. Say when it from an axial state, when it jumps to a ground state or lower state, it emits. So that is why it is called, it emits a radiation, but as you see here, Pennsylvania is called emission spectrum. Okay, so you have two spectrum, one is emission line spectrum, and also we can see that when a line is unstable, then the electron goes from a lower to a higher state, the photon is absorbed by the atom, and that is called the absorption spectrum. Okay, so this is a simple picture. You have sunlight, which will have there with the wind, and then suppose you had a cloud of pillar gas somewhere. Okay, Say the light is kind of suppose you are looking at the one which is going straight here. Okay. Of course, you are going to remove everything. So let's start with this one. So this light which is coming directly from the source, if you look at the spectrum, you get a continuous spectrum like this. Okay, with the five colors. I'm showing only visible because I can show you only visible. Everything else is there on that side. Right? We have X-rays, infrared, UV, gamma rays, everything else there on that side. But I can show you the color. That's why the little geo is here. Okay? So the little geo is here. So you can see that the light which is coming from the stairs, you have all the wavelength. Okay, without any obstruction in between. Yes, I think there is some kind of a gas here, which is hydrogen gas, for example. Okay, we can't any gas, but it's hydrogen gas. And if you look at that, I say it's the light against the cloud, and you can just look at this spectrum, you see that from this one, some lines are missing. Same wavelengths are missing. So these dark lines are missing wavelength for this spectrum. And this is called absorption spectrum. So these wavelengths are absorbed by the atom, and then only stay here like that. Okay, which is present here. And these are to be characteristic of a particular atom. So if you look at the wavelength, so I visibility knows particular wavelength. There be on how particular wavelength and so on. So looking at the wavelength, we can try to find out what kind of an element is present in this gas cloud. Right? Now if you go and look, so this is looking at still, right? Which means that is the line which is coming from the source. What thing you are looking at, but is going to look that's all. But if it's not in the straight line, because this is cut off, you see the scattered light. That is, so this cloud will emit some light other than what you have here. And this is the emission spectrum. So it's the dark, and you have some lines, which is the color. And that will be the emission spectrum. So this is the absorption, that is from down lower state going to a higher state, but in an absorption spectrum, this is an emission after, an exciting the atom, after some time, it will re-excite to a lower state, radially light. Okay, so this is the emission spectrum. Clear? So this is what we are going to look at. Now, of course, by looking at those atom body, and then I'm going to quickly go through because this is not, I think probably you would have all done this. Okay, but just for the sake of the introduction part, I'm trying to just call up the theory, the same theory, which you already know, and that will come to the energy level. That's the idea. And we also find out the energy of the spectrum and then try to, compare it with the wavelength and say where are the wavelength which is coming out. Okay. So this is something which you already know. We had electron moving around, and there is an electrostatic attraction between the nucleus because it's positively charged, and the electron which is negatively charged. And that it is stable, the electron is stable only in these potentials are equal. Okay. So obviously these are one PA, but it is just pure of this. So you can find out the velocity from this. Okay. And then this is the ionization burning, Rosnet. If you use that, which is MER is NHK is the angular momentum, and then you can put the velocity here, and when your RM, you get NH cross, which you can simplify with mv with squared r by squaring it, we get n squared h cross squared, where h cross or h bar, whatever you call it, and usually call it h cross, which is the reduced Planck's constant. That's by 2 pi. Okay, so if you simplify this, you can find the Rn, which is the millimeters. Now, obviously, then more atom body, you can find the radius. But quantum mechanically, you cannot. Right? You can get an expectation value as well only. So you can clear with it very well, and then you can write in terms of n squared by z, h squared, epsilon naught pi e squared, where epsilon naught is the permittivity at vacuum. Considering the constants. So you can actually find out the value of Rn. And If you substitute Rn with n0, which is quite a band radius, which is h squared epsilon naught by m e squared, you get n squared by z n0. Okay. So if you're hydrogen atom, when it's ground state,
So what that means?
Rn will be R0, n is 1, z is 1, you get n0. So that scientist Bohr radius comes into, that is the radius, approximate radius of the high electron in hydrogen atom, the ground state. Okay. So that's the definition now. And of course, you play with this a bit, we can find out the value of the so that's the value is 0.529 Einstein, which you can find out from these constants. You can give that input and then find out. So this should be one of the details. We'll do that. And here do that. Okay? Okay. Made it. So yeah. So the R1 H, that is the ground state hydrogen atom radius. Okay. Again, you can find out the, of course, you can take energy or potential energy, and then you can find that the energy will be given by this particular expression, which is also something you might have seen earlier. Okay. Now, this is not just a hydrogen atom, this is for hydrogen-like atoms. So can we name hydrogen-like atoms? You have hydrogen, what else?
Methyl.
Helium,
Helium.
helium plus, with your nucleus, and so they are all hydrogen-like atoms. And you can solve the same the energy for all these atoms using the same expression. Then you just put the Z value as the atom. Just okay. So this is your energy, and you can very obvious. Maybe you have the radius, so this is a question which you have done earlier, and you can substitute it here, and then you can write the name at hydrogen like the electron in an hydrogen like atom as this particular expression. And you can see that it's all constant except the Na. And this Na is nothing but the density counting number, which basically defines the energy levels of an atom, the principal energy levels. And of course, you will see that I've said levels and so on later in other lecture. Okay? And this is another exercise I want you to do it, which is the finding out the energy for hydrogen like that. Okay? And you will find that this constant will be 13.6 electron volt. Okay? So for ground state hydrogen atom, the energy of the electron is minus 13.6 kilowatt. Okay? Now, if this, why it is negative? It's a tendency, but I know called NATO.
And person not inserted.
Now, attractive, but in this case, you talk about it's a bound state, because the electron is bound to the nucleus, so it is negative. There is not possibly if it is repelling atoms scattering away. So, if you talk about a positive energy, it means it is moving out and it is unbound. Okay, so when you draw the information energy curve, if it is just above the well, then it is positive and it can go on. But if it's within the well, then it is bound within that particular well. Unless you give the energy of the height of the well, it will be trapped or bound to the system. So that's the negative. Okay, so now if you look at the energy of a transition, this is how we are coming to the spectroscopy. You want to look at the energy of the line which is emitted. So we are looking at, say, emission spectrum. Okay. So now if you look at this, delta E is a higher energy level, which you normally write as N prime, minus En. So where N is greater than N bar. Okay. So basically it's a transition from a higher energy level to a lower energy. So electron is excited, and when it comes down, this energy will decrease, which is very much extreme of the new potency left by lambda, where lambda corresponds to the wavelength of the light emitted by the electron, by the atom, doing the transition from higher state to a lower state. And this is the same energy, but the n is different for both energy noise. Everything else is same. So 1 by n prime square minus 1 by n square. Okay. So this is something which you already seen. And this is the energy level, energy of the emitted photon. Okay. Now we can write it, we can simplify this like this, and then which is nothing but, because I've taken the H and C here, and you get the 1 by lambda. Okay. And we know that 1 by lambda is wave number. It's called the wave number. Now I'm defining wave number here because most of the spectroscopists or astronomers use wave number as the energy. Okay, because this is in terms of energy itself. Okay, so they, instead of using lambda or frequency, they usually use wave number and in centimeter inverse. So you will see in most of the examples or problems or wherever you see, the energy is written in terms of centimeter inverse. Okay. So another exercise is, how do you go from 1 electron volt to 1 centimeter inverse? Okay. You can use this expression. This one here. Hc by lambda. It's battery weaker. Okay. Now, if you look at this particular expression now, this is the wave number, which is 1 by lambda. So, I mean, how does centimeter inverse come into picture? Because lambda is in terms of the 1, which can be meter or centimeter. You usually do it in terms of the twin as the pen. No, where's the pen? Yeah. So, this is in, say, if you write it in terms of meter or centimeter inverse. So lambda will be in centimeter, so this will be in centimeter inverse. So this is how the wavelength, the wave number is written in terms of the inverse. And this particular quantity, which is a constant, so if you take z square outside, the rest of the terms, they are constants, and that is how the Rydberg constant. But of course, it is not simple. Have to remove this. Get lost. Now this won't work. I have to close this. Oh. Although when it works, then there is no point of the pen.
Hell.
Yeah. Okay. So, yeah. So, right. Okay, so what we have is R infinity is the Rydberg constant, and this is the Rydberg constant for a theoretical nucleus of infinite mass. Now, the reason being, we have taken the mass as the mass of electron. So when you take mass as mass of electron, then we are assuming that the mass of the nucleus is infinity. And that's how we get this R infinity. Then, of course, we know that we have to use something like this, the reduced mass, because we need to consider the nuclear mass along with the electron mass. So this is electron mass, this is the nuclear mass, which is MeMn by Me plus Mn, which is the reduced mass. So if you use that here, mu instead of m, you get a different expression. So we can simplify this. So this is the reduced mass which we have here, and then you can separate this. This part is actually your R infinity. Okay? So R infinity by, and then if you divide by Mn, you have 1 plus Me by Mn. And S is the Rydberg constant for hydrogen atom. So the mu will vary depending upon the nucleus or depending upon the element. If it is hydrogen, we have 1 proton, 1 electron. But if it's, say, an isotope of hydrogen, right? Say deuterium. Deuterium, the nucleus is different, right? What is the nucleus of deuterium? You have 1 proton because atomic number is 1 and 1 neutron. So now the Mn, the nuclear mass is not same as the nuclear mass of the hydrogen. So you need to use that. Okay. So this is going to change depending upon the nucleus, and it will be different for each element and each isotope of each element. Okay. So what we have is RH, you can write as this particular fan. Now, so this is another exercise. Okay. Finding R infinity and RH and how much it varies. Okay. All right. So now we have the wave number, which is, and as I said, the energy of the line which is coming out is represented in terms of the wave number. And you can write in terms of this is the expression we have. And you can see that RH is a constant. So what changes is the N and N prime. Okay. Now, so what you have is N is the lower state because N is less than N prime. And N prime is, say, for example, if you take this particular state, excited state, which is N equal to 6. So 1 by 2 square minus 1 by 2, which will give you, with the Rydberg constant of hydrogen atom as this, you can find it will come out to be 410 nanometer. Or wave number T4390 to 0.24 centimeter inverse. So this is this particular line, which is experimentally proven. So the Bohr atom model works very fine for spectroscopy, for an atomic spectroscopy. That's the reason I just brushed upon the atomic spectroscopy part, the atomic part, to come out with the idea of these expressions. And this works very well, and this can be used to verify experimental observations. Okay. Well, we looked at the visible spectrum coming out from the hydrogen atom, and we said it's the Balmer series. But as I said, that is not the end, right? You can see that there are so many. So this is the line which we talked about, N equal to 2. So N equal to 2 is the lower state, and anything coming from a higher state, you can, this is called the Balmer series. So this is the visible series. So, violet, blue, and blue, green, red, and so on, you can see it here. And this is called the Balmer series. Okay. But you can also have the line, the spectrum, which is due to the emission of line between two higher state and N equal to 1 state. Okay. And this is, come inside. Come. So when the electron falls from a higher state to N equal to 1 state, the energy is released, and this is in the ultraviolet region, and this is called the Lohmann series. And then for N equal to 3 as the lower state, we have Paschen, and so on. So this is the hydrogen spectrum. So the hydrogen spectrum is not simply the visible spectrum, but we have so many other series. So this is called the hydrogen series. So you can look at, it's the same picture, but in a different way. So you can see that this is not ordered. So any line due to the, transition of an electron from a higher state to N equal to 1 is Lohmann. From a higher state to N equal to 2 is Balmer. From a higher state to N equal to 3 is Paschen, and so on. So this is actually the hydrogen series, various hydrogen series, which you normally see in a hydrogen atom spectrum. Okay. So if you look at the, of course, the first line series which was observed was in 1885. And as I said, the reason is very simple, because it's the visible region. So, and then we have other series, Lohmann, which is in ultraviolet, which is to the N equal to 1 lines, all the lines. So it's not a single line. There are so many. That is why it is called a series. And then Paschen, which is to N equal to 3, which is also in infrared, which is observed in 1908 by Frederick Paschen. And then to N equal to 4 is called Brackett, which is by Frederick Brackett. in 1922, which is also an infrared. Then N equal to 5 is the Funt series, so it's by August Hermann Funt in 1924. And then N equal to 6 is by Humphreys in 1953 and so on. Okay, so I've shown 6 series here. So I think the other series are very difficult to observe because it's too, you'll see that it's already reached 3282 to 12370. It's the higher end. Okay. Now, yeah, just one more thing which I need to mention here. So this is the Lohmann, this is Balmer, right? This is N equal to 1, this is N equal to 2. So this is Lohmann and this is Balmer. Now, there are some notations which you should understand. Because whenever you see, you don't say Lohmann is Ly alpha means the first line, right? So the lower level is N equal to 1. So alpha is from N equal to 2 to N equal to 1 is called Lohmann alpha. The next line is called Lohmann beta and gamma and so on. Okay. For Balmer, you don't say Balmer alpha. But historically, since it was observed very early, it was called hydrogen alpha. Okay. So because other lines were not known at that time, so it is simply called H alpha. So whenever you say H alpha line, it means the first line, that is N equal to 3 to N equal to 2 transition, the line because of that reason. Okay. Or hydrogen beta and so on. And then this is also Paschen alpha, Paschen beta, gamma, and so on. So whenever when a problem comes, probably a problem might come in the examination, like PA alpha line. So you should know what this PA alpha line is. So we'll see that alpha is the first line, say N equal to 4 to N equal to 3. So you should know the N of that particular transition, the N's, N and N prime. Okay, that will give you the energy, right? That will give you everything else. The wave number, the energy, frequency, whatever you want to find out, you can find it from that particular transition. So that's this. Okay, and how do you? So this is how you get a spectrum. Okay, spectrum is when you have a piece of paper where lines drawn it. Okay, so the spectrum will look like this. Okay, with wavelength as the x-axis or wave number. Here this is a picture I just copy paste from somewhere. Okay, so but usually you will see in wave number. Wave number. Here it's written in wavelength. You see in both wavelength and wave numbers, mostly in wave numbers. So each transition is represented by one line and with particular wavelength. Okay, so for example, this line is Balmer alpha. Okay, so by looking at the wavelength, you can find, okay, so this is the alpha line corresponding to the Balmer series. Okay, clear? Right. Okay, now when we talked about the Bohr atom model, we said, okay, there is a line which you saw, this Balmer series, Lohmann series, Paschen series, and so on. You say transition, and you say, okay, you got the spectroscopy. But unfortunately, that is only the beginning. Okay, the reason is very simple. This is called a growth structure. Sorry. So this is called a growth structure, and this particular line is one of the series line, say H alpha. But then that is not the entire scenario. That is not complete. That is not because you will have some magnetic field created because of the motion of the electron, or you can also give field to the system and so on. So whenever there is a motion, magnetic field will be created, and that will create some additional line which is called fine structure of hydrogen atom. Now I'm talking about only hydrogen atom. Okay, and you can see that instead of a single line, in this case, we'll see 3 lines here. And the reason is, you will see that because of the quantum numbers. They state different quantum numbers. We have principal quantum number, and then we have the L, which is the magnetic quantum number. Sorry, orbital quantum number, and then Na, the corresponding magnetic quantum number. And we know that L, which is the orbital quantum number, can go from 0 to n minus 1. So suppose the principal quantum number n is 3, you have 0, 1, and 2. So there will be 3 L's, and so on. And for each L, you can have ml going from minus L to plus L, 2L plus. So in this case, suppose L is 1, then it will split into 3 sub-levels. Okay. So instead of seeing one particular level, you will see 3 lines. And in this case, L equal to 2, you see that one line will split into 5 lines. Okay. Here, the magnetic field is not equal to 0, and the additional terms like spin-orbit interaction, because there is a spin of the electron and then orbital motion, and there is a coupling between them. Okay. We will see that maybe the last part, how does that work? And then you can have all these different levels because of that. And of course, there is something called a relativistic correction, which is also comes under fine structure. Well, what do you mean by relativistic correction? Yeah, because the electron is moving quite fast. The derivation we used is the speed of the electron, which is classical. But you need to include relativistic motion of the electron, and then find that will add to the energy of the system, the energy of the transition. So you'll have a E, suppose E1 is the energy of the E1H, say first transition. There will be an additional delta E added to it because of the relativistic correction. Okay, and we will not go into the derivation of this. You might have studied in your MSc, or you will study it in MSc in the. Where did you study that? Do you remember? Perturbation theory. Okay, you will study the time-independent perturbation theory. You will study that, where you will find that there is a term which you need to add to the energy to get the total energy of the system. Add or subtract. Add is vectorially, I mean. And finally, when you have nuclear interaction and when the large external force, you have additional lines, which is hyperfine structure. Okay, there will be a shift in the spectrum. Okay, so that you will see, that also you will study when you go into the spectroscopy later on. So this will be the energy level. So as I said, when you solve hydrogen atom using Bohr atom model or Schrodinger picture, which we will see in the next class, that's not the end to it. That is only the beginning. And then you will have additional terms coming into the spectroscopy, which needs to be considered, because you will see that there is a change in the spectrum regardless of the theory you have already used and the spectrum you already have, which proves very well. But then you will see when you have additional terms come into picture, because of these reasons, there will be a shift or there will be a split. And you need to account for that using other theories. And then, of course, I think probably we will stop the lecture, first one, before we have a break. In 1926, Schrodinger came up with the idea of cloud model, which looks something like this. Okay, so this is the Bohr model, and this is the Schrodinger electron cloud model. Now, where is the radius now? Now, obviously, of course, this is just an artistic picture. It's not exact, but you can understand the idea behind it. It looks something like this, which means the probability of finding electron anywhere in the space is not zero. That's quantum mechanics, right? There is at least a finite probability. Even if it is very small, even if it is very close to zero, there is a non-zero probability. Because it's a wave function, it's a wave, it is everywhere, which means it should be there anywhere. So there is a probability, even if it is very small, to find an electron somewhere here. So that means it is not in a path like this. So if you look at the picture, so this may be a better picture. So this is a ground state, and this is an excited state of hydrogen atom. So this dashed line is basically the Bohr radius. And if you can, and it is not bad, because if you look at the picture, you will see the electron mostly around that region. Even though electrons are present everywhere, you'll see that electrons are mostly around that particular line. So Schrodinger said that, it's a wave. Heisenberg said that it's uncertain. It can be anywhere. It's everything. It's a probability. Nothing is exactly measurable. So then you are looking at finding electron anywhere in the space, which means you should be able to see something like this. But then when you measure it, you get something very close to this, because out of 100 times, maybe 70 times you get this particular value or close to it. And this is the excited state, where the electron is in an excited state, and you see this will be the radius, most probable radius, which you can get as the expectation value of R in quantum mechanics in the bracket, right? You know what is bracket notation is, right? Yeah. That's it. So if you have any doubt, you can ask me now before we end the lecture. Anything related to this before we go into the next part? Right. Okay. Okay then. So I'll be here around. So if you have any doubt, you can ask me anytime. Okay. Okay. Thank you. We'll stop here.